Welcome to G Fun Facts Online. We all know what solar panels and wind turbines look like. They're the symbols of our renewable energy future. But what if I told you there's another solar technology, one with no moving parts, that works in silence and is on the verge of a massive breakthrough? Today we're talking about the Solar Thermoelectric Generator, or STE. It's a remarkable device that turns heat, any heat, but especially solar heat, directly into electricity. For decades, it's been a niche player, held back by low efficiency. But that's all changing. In this episode, we'll dive into the incredible science of STEGs, the revolutionary materials making them better, and the groundbreaking advancements that could soon have them powering our world in ways we never imagined. Let's get started. The magic behind every solar thermoelectric generator is a phenomenon discovered way back in 1821 by German physicist Thomas Johann Seebeck. It's called the Seebeck effect, and it's surprisingly straightforward. When you take a specific type of electrically conductive material, heat one end, and keep the other end cool, an electrical voltage appears. An electric current starts to flow. Why does this happen? It's all about the behavior of charge carriers inside the material. In some materials called N-type semiconductors, these carriers are electrons. In others, called P-type semiconductors, the carriers are holes, which are essentially the absence of an electron. When you apply heat, the charge carriers at the hot end gain kinetic energy. They get excited and start to move, or diffuse, towards the colder, less energetic end. This migration creates a separation of charge. You get a buildup of negative charge at the cold end and a net positive charge at the hot end. This difference in charge is what we call voltage. A practical thermoelectric generator is a bit more complex. It uses many pairs of these N-type and P-type materials shaped like little legs. They are connected electrically in a series, like links in a chain, to add up the voltage from each pair. But thermally, they are connected in parallel, meaning they all share one hot side and one cold side. You place the hot side against a heat source, like concentrated sunlight, and the cold side is attached to a heat sink, which dissipates the heat and keeps that crucial temperature difference alive. Without a temperature difference, there's no voltage. Now, how do you measure how good a material is at this? Scientists use a value called the figure of merit, or ZT. Think of it as a materials report card for turning heat into electricity. A higher ZT means higher efficiency. To get a high ZT, a material needs a very contradictory set of properties. First, you need a high Seebeck coefficient. This means you get a lot of voltage for a given temperature difference. Second, you need high electrical conductivity. The electricity needs to flow easily through the material with minimal resistance, just like in a good metal wire. And third, this is the tricky part, you need very low thermal conductivity. You don't want heat to easily flow from the hot side to the cold side. If it does, your temperature difference shrinks, and so does your efficiency. You want the material to be a good electrical conductor, but a poor heat conductor. This is the central challenge. Materials that are good at conducting electricity, like metals, are usually also great at conducting heat. Materials that are bad at conducting heat, like glass or wood, are terrible at conducting electricity. For decades, scientists have been on a quest for a material that breaks these rules, something they poetically describe as a phonon glass, electron crystal, a material that allows electrons to flow freely like they're in a perfect crystal, while blocking the flow of heat, or phonons, as if it were a disordered piece of glass. For a long time, a ZT value of around 1 was considered the benchmark for a practical material. But thanks to recent breakthroughs, some lab materials are now pushing ZT values past 2.5, which is a huge leap. This quest has led researchers to explore a whole pantheon of materials. For decades, the field was dominated by a few stalwarts. The workhorse of the group is bismuth telluride. It's excellent for applications near room temperature, up to about 250 degrees Celsius. You'll find it in small thermoelectric coolers and in systems that recover low-temperature waste heat. Recent designs have pushed its conversion efficiency up to 8%, which is a big deal. The main drawback is that tellurium, a key ingredient, is quite rare, which could limit large-scale production. For higher temperatures, between about 200 and 400 degrees Celsius, scientists turn to lead telluride. This is the material that has powered deep space probes in their radioisotope thermoelectric generators, or RTGs. By tweaking its composition, researchers have achieved incredible ZT values as high as 2.2. The obvious problem, however, is the toxicity of lead, a major environmental concern. Another classic family of materials are the scudarudites. These have a fascinating, complex crystal structure that looks like a cage. Scientists can fill this cage with other atoms. These guest atoms rattle around inside the cage, and this rattling is incredibly effective at scattering heat-carrying phonons, which slashes the material's thermal conductivity, all while the cage structure itself maintains good electrical conductivity. Scudarudites are great for mid-temperature applications and have shown ZT values over 1.7. But the most exciting advancements are coming from the world of nanotechnology. By engineering materials at the scale of billionths of a meter, scientists can fundamentally change their properties. Creating nanostructured materials with features like nanoparticles or nanowires introduces countless tiny boundaries within the material. These boundaries are fantastic at scattering phonons and stopping heat flow, but they let electrons pass through relatively undisturbed. This strategy has been used to dramatically improve materials that were previously considered terrible for thermoelectrics. Take silicon, the stuff in computer chips. It's a great electrical semiconductor, but it also conducts heat extremely well, giving it a very low ZT value. However, by structuring it into nanowires, researchers improved its thermoelectric performance by a factor of 3.5 at high temperatures. Taking this even further, scientists are now working with quantum dots. These are semiconductor crystals so tiny, just a few nanometers wide, that they start to obey the bizarre rules of quantum mechanics. The movement of electrons becomes confined in all three dimensions. This quantum confinement can lead to a significant boost in the Seebeck coefficient, one of the key factors in a high ZT value. While better materials are crucial, the overall system design is just as important. And this is where one of the most exciting recent breakthroughs happened. Researchers at the University of Rochester announced they had increased the power output of a STEG by a factor of 15. And they did it not by inventing a new material, but by rethinking the hot and cold sides of the device. Here's their three-pronged strategy. First, on the hot side that absorbs sunlight, they used a special black metal. They created this by blasting the surface of tungsten with extremely short, powerful laser pulses. This etched nanoscale structures onto the surface, making it almost perfectly black, meaning it absorbs nearly all incoming sunlight while minimizing heat loss. Second, to trap even more heat, they simply covered this black metal with a piece of plastic, creating a miniature greenhouse effect right on the device. And third, on the cold side, they used the same laser etching technique on an aluminum surface to create a microstructured heatsink. This micro-dissipator dramatically increased the cooling capacity, making the temperature difference across the device much larger. This focus on thermal management, rather than just the core material, was a paradigm shift. Other system-level innovations are also pushing the technology forward. Concentrated solar thermoelectric generators, or STEGs, use mirrors or lenses to focus a large area of sunlight onto a small thermoelectric device. This intensifies the heat and boosts efficiency. Researchers have already hit 7.4% efficiency with this method and believe over 15% is achievable with today's materials. If you combine STEGs with thermal storage, you could have a reliable, silent, 24-hour power source. But Perhaps the most promising approach is creating hybrid systems. One of the biggest problems with standard solar photovoltaic, or PV panels, is that they lose efficiency as they get hotter. So, what if you attached a thermoelectric generator to the back of a PV panel? The TEG would capture the waste heat that is normally lost, converting it into extra electricity. This not only boosts the system's total power output, but also actively cools the PV panel, making it more efficient. Studies show these hybrid PV TEG systems can increase the overall conversion efficiency by anywhere from 8 to 23% compared to a standalone PV panel. So with all this progress, what's holding STEGs back from being on every rooftop? The main hurdles are manufacturing cost and scalability. However, new techniques are emerging to tackle this. Additive manufacturing, like 3D printing and screen printing, allows for the direct printing of thermoelectric materials onto different surfaces, even flexible ones. This opens the door to wearable electronics that are powered by your body heat, or buildings covered in power-generating skins. Economically, STEGs are still catching up. A 2023 study found that the cost per watt for a thermoelectric generator was still about 3.5 times higher than for a standard solar panel. But the market is growing, projected to double from about $800 million in 2023 to over $1.6 billion by 2030, driven by demand in waste heat recovery, especially in the automotive industry. As manufacturing scales up and efficiencies continue to climb, this cost gap will shrink. Finally, there's the environmental impact. STEGs are often called a green technology, but we have to look at the entire life cycle. The impact depends heavily on the materials used and the device's efficiency. A low-efficiency generator made with energy-intensive materials might not be a net win for the environment. And the use of toxic materials like lead is a serious concern that needs to be addressed by developing new, eco-friendly thermoelectric materials. The field of solar thermoelectric generators is at a turning point. After decades of slow, steady progress, a wave of breakthroughs is unlocking their true potential. The future will likely see even higher efficiencies, driven by smart thermal management like the black metal technique. Hybrid systems that pair photovoltaics with thermoelectrics will likely become the standard for high-performance solar. We'll see flexible and wearable devices silently generating power from waste heat all around us. And as the technology matures, there will be a greater focus on sustainability, using abundant, non-toxic elements. Perhaps the most exciting prospect is the democratization of energy. Because STEGs are solid-state devices with no moving parts, they are incredibly reliable and require almost no maintenance. They can be deployed anywhere, from remote villages to urban skyscrapers. The journey of the solar thermoelectric generator has been long, but its future has never been brighter. We're learning to harness the heat of the sun in more ways than one, giving us another powerful tool in the fight for a sustainable future. Thanks for tuning in to G Fun Facts Online.